Today we're going to be talking about RLC circuits, so circuits with a resistor, an inductor, and a capacitor. And these are also a particular filter that we can use to essentially let signals through or to notch signals out. We'll start by talking about a simpler circuit, which is simply an LC circuit, where we have an input voltage, an inductor, capacitor, and the output. And we'll take the output across the capacitor. And this is a standard circuit, and we know that the gain of this circuit is simply the impedance of the capacitor over the impedance of the inductor plus the impedance of the capacitor. So simple gain circuit here. And this we know the impedance of a capacitor is 1 over j omega c. Of an inductor, it's j omega L, and then plus 1 over j omega c. So there's the gain of this circuit. So the output voltage is going to be this complex number times the input voltage. And that looks a little nasty, but we can simplify it. We can basically bring this out. So we multiply the bottom by j omega c. It's going to cancel this factor out. It's going to fold in there. And we're going to get that the gain is going to be 1 over j squared omega squared LC plus 1. So I'm just multiplying that through. And we can now, that LC combination has units of inverse frequency squared, so we can define a characteristic frequency. Omega LC squared is 1 over LC. So we'll make that definition. And noting here, the j squared is minus 1, so we're going to get a 1 minus that quantity, and we'll have the gain is 1 over 1 minus omega squared over omega LC squared. So there's the gain, and it turns out that's a real number. It's kind of interesting. We've got two components, purely reactive, and we get a real gain here. Another interesting thing about this, if the frequency is equal to the characteristic frequency, this quantity is 1. We're dividing by 0. We're going to get an infinite number. So the output voltage is going to be infinitely larger than the input voltage, which is interesting as well. So we get some huge gain. We can look a little more carefully at this. We can take a couple of limits of this just to see what's going on. So if omega is small compared to this frequency, so this is a small number, then omega is small, this is going to be basically nothing, and the gain is going to go to 1. So for low frequencies, it just lets the signal through. It doesn't do anything. Just a factor of 1. If omega is large compared to omega LC, so this becomes a big number, then that part doesn't matter. So we have minus 1, and we're just going to get the omega LC up above. The gain is going to go to minus omega LC squared over omega squared. So it's going to fall off like 1 over omega squared. On a Bode plot, that means it's going to have a slope of 40 decibel per decade. It's going to be falling at 40 decibel per decade. So if we look at a Bode plot of this, 20 dB log of the gain versus the frequency, and here is omega LC. Low frequencies gain is 1. We're 0 on here, so we're going to come in with 0. At some point it's going to shoot up to infinity and then come down and fall off at 40 dB per decade with this huge gain right here, which we believe spikes to infinity in this particular case. So that's what happens when we have simply an LC circuit. We'd now like to extend this a little bit and go to and add the resistor to this. Let's change that circuit ever so slightly. We'll have our input voltage. We'll have our inductor. We'll put a resistor there. We'll have a capacitor here. And we will continue to take the output across the capacitor. Okay? And this is exactly the same thing we had before. The gain is just going to be the impedance of the capacitor over the resistor plus the impedance of the inductor plus the impedance of the capacitor. So all these components here, and so we just need to work that out. And that's not terrible. We did part of it already. Gain is 1 over j omega c for the capacitor, the resistor plus j omega L plus 1 over j omega c. Okay, so we can do the same sort of simplification we did before. We can bring this down, we can factor the r out. Before I do that, I'm going to remind ourselves omega LC is 1 over the square root of LC like we defined above. And we recall from earlier that the RC is 1 over RC. And if we do that, then we can do some algebra. The gain is now a little bit more complicated. So we've got the same piece we had before, but now we have a piece which is j omega over omega RC. So here's the piece we had with no resistor, and omega RC has the resistor in this, so here we get a piece, and now we have a complex number, a real part and an imaginary part, and this part here. If the resistance goes to 0, then for R goes to 0, 1 over RC goes to 0, so this term goes away. We get back to what we had before, so that's good. But we get a slightly different form of the gain there. And to look at that, what we need to do is we need to take the magnitude of this gain, which we can do. It's just 1 over, and we got this square root down here of 1 minus squared, and then plus omega squared. So there is the magnitude of the gain. And now we also are interested in the phase, so the tangent of the phase. So the trick here is we look at this number here. We want to put the top, the j in the top, so we multiply it by the complex conjugate in the bottom in the top, so that's going to give us this thing with a minus sign here, and the denominator is just going to be this squared, so the whole thing is going to be this minus that in the numerator. So we simply get the tangent of the phase is going to be minus omega over omega RC from that term divided by 1 minus omega squared over omega LC squared. So there's the magnitude of the gain and the phase here. Now, when omega equals omega LC, this is when we went to infinity before, this term goes to 0, but we still have this term left over. So let's look at those things. At this characteristic frequency, omega LC, where it blew up before, now we're left with the gain just being given by, go back down, the last part of that term there, so it's going to be omega RC over omega LC, which is square root of LC over RC. So there's the magnitude of the gain that we have there. We'll make that magnitude. And the phase is going to be, now we're going to get minus omega LC over omega RC over 1 minus, so now we're going to get this 0 here, and there's a minus sign here. So this is 0, so it goes to infinity. There's a minus sign here. So if we look at the quadrants, this is that's going to be either the third or fourth quadrant. So it's going to be minus 90 degrees. 90 degrees at this particular case. So we get a finite gain. We're 90 degrees out of phase here. That's kind of interesting because if we're 90 degrees out of phase, we don't get any power there, so there's no. Now we can look at a couple of other limits of this as well. We can take the limit as omega goes to 0, and we go back and look at that up here. As omega goes to 0, that term goes to 0, that term goes to 0, the whole thing just goes to 1, so the gain goes to 1, like before. And the phase, as omega goes to 0, we're going to get minus 0 over 1, so it's going to go to 0. And if we take omega much larger than omega LC, then we go back up to the gain. This term wins because it's to the 4th power, so all that's going to be left is that. We're going to get omega squared over omega LC squared. Squared over omega squared. So it's going to fall off like 1 over omega squared, and the phase is going to go, okay, so, and the phase here is going to go to, it's going to be dominated by the 1 over omega squared here, so it's going to go to 0, which means 180 degrees, so the phase will go to 180 degrees. So if we look at this on a Bode plot, we'll have frequency 0, 20 dB log of gain, omega LC. Starts out a gain of 1, so we're 0. We go up to something here now, but now it's finite. And then it's going to fall off and fall with 40 dB per decade. And the phase is going to go from 0 to minus 180, minus 90. That's going to happen here. It's going to start out at, it looks something like that. So it's going to start at 0 and then go to 180. It'll go through 90 degrees at that resonance point there. So that's basically what happens with an RLC circuit when we look across the capacitor. We could look across other components, and we can actually invert this and create notches instead of amplification at the signal. But you can do a lot of interesting things with an omega LC, with an RLC circuit here. Key thing is eventually the gain will fall off at 40 dB per decade. It falls off like frequency squared. That's different from the high pass and low pass filters where we fell off like 1 over the frequency or rose with frequency. So this is a sharper cutoff, so that might be good. So you can get a better filter or a sharper cutoff with this. And then you have the region where you have a gain here that can be very, very large. So you can get a big output signal from a small input signal for basically this characteristic frequency here.